In this question, we are asked to calculate the efficiency of the pump, with the efficiency of the motor given as 0.9. We can consider the inlet to the pump as 1 and the outlet from the pump as 2. First, let's establish some definitions that will need to solve this problem. Efficiency can be defined as the desired output divided by the required input. For the efficiency of the pump, we can express it as the mechanical energy in the fluid stream divided by the shaft work input to the pump. We can represent this equation as follows. Similarly, the efficiency of the motor can be defined as the shaft work output divided by the electrical work input. The electrical work is the input to the motor, which is 35 kilowatts, while the shaft work is the same as the shaft work used in the efficiency equation for the pump. In these equations, I used the rating form for work and mechanical energy with a dot on top of the letter. Therefore, accurately speaking, they represent time derivatives and hence should be referred as power. However, for convenience, I am referring to them as energy and work. The mechanical energy equation encompasses the addition of pressure energy, kinetic energy, and potential energy. The change in mechanical energy from state 1 to 2 can be expressed as such. To convert this into the rate of total mechanical energy change of the fluid stream, we can multiply the specific mechanical energy change by the mass flow rate of the fluid. Additionally, we need to establish a relationship between the volumetric flow rate and the velocity of the fluid. If the cross-sectional area of the tube through which the fluid is flowing is denoted as A, we can express the relationship as the volumetric flow rate being equal to the average velocity of the fluid multiplied by the area. We also know that density is equal to mass divided by volume, and we can establish a relationship between mass flow rate and volumetric flow rate using density. Our plan is to use the efficiency equation to calculate the mechanical efficiency of the pump, utilizing the value of shaft work from the efficiency equation for the motor. To do this, we have the efficiency of the motor and the electrical work input to the motor. We also need to calculate the rate of mechanical energy change through the pump, and we can determine the mass flow rate using the equation m dot equal sign rho v dot, where v dot is calculated using the relationship between V average and the area. First, let's calculate the W shaft, and then we'll proceed to calculate E mechanical energy using equations 3 and 4. Since the pump is a relatively small device, we can neglect potential energy changes, and using equation 5 we can calculate the fluid's velocity at the inlet and outlet. Let's rewrite the mechanical equation assuming that the potential energy change is 0, and then substitute everything we know. The pressure change from 2 to 1 is 400 kilopascals, and we've calculated the velocities now. Let's check the units. In the first part we have pascals. Let's convert that into Newton meters. In the second part we have kilograms meters. Let's convert that into newtons as well. So in this case, we convert everything into Newton meters. However, the first part is in kilonewton meters. Let's convert that too. Finally, we can convert this into energy terms with the understanding that 1 Newton meter is equal to 1 joule by definition. So let me present the unit conversion once more. And the units cancel out to kilojoules per second, which is equivalent to kilowatts. This represents our E dot mechanical. Now let's calculate the efficiency of the pump, which is found to be 83.6%. To simplify calculations and avoid complex unit conversions, it's helpful to note that the units of pressure energy, pascals meter cube per kilogram, and kinetic energy, meter squared per second squared, are equivalent. The units of potential energy are also meters squared per second squared. The challenge arises when dealing with pressure units, which are often in kilopascals like in this example, not pascals. Consequently, the pressure energy term in the mechanical energy equation is expressed in kilopascals meter cubed per kilogram. To align units, you should divide the kinetic energy and potential energy terms by 1000 to express them in kilojoules per second terms.